into the machine transform information, and there is like some kind of pattern recognition, neural network, some algorithm, and then it will be produce some diagnostic information. So that information can be used by doctor or technician, like scientists those are using in medical industry. So that way we can help drug discovery or some kind of diagnostic information used by the doctor. So this is like general block diagram. So today what we are going to discuss about medical imaging. Then we are going to have like little bit of introduction, what exactly medical imaging, how the images are captured. Then we are discussing about image denoising, like the which is challenging task in terms of a medical imaging area, because most of the images are in a black and white. It's mostly like gray image scale. So how we can interpret and how to denoise that. And then yesterday we already saw the CPU GPU comparison, but today I'm giving a little bit more detail about the latest GPU available into the market, and then what are the architecture features. Then we can talk on that. Then some kind of computer vision for the feature extraction for the microarray image. Like yesterday we discussed what is a computer vision. So similar technique is used into the feature extraction. So that way we can get good accuracy of the parameters. And another example is like hand finger counting application for the deep CNN algorithm. So basically I am showing how we can use CNN for getting my hand finger counting effectively, so that we can understand how much layers, how the accuracy is going to be improved. And then finally we have the another example of medical image classification using CNN. So the same CNN network, how can we translate into the deep network, so that we can going to discuss. So now give me about the introduction, like what exactly the medical imaging. Like nowadays, the modern medicine is like, if you visit any hospital or any doctor, they usually ask you like go for the X-ray or go for some kind of more detailed like CT scan or the MRI, or some more information is requested by the doctor, because they don't want to, like inside the body they're not able to see all the detail. So they want like some kind of internal picture. So that's why the diagnostic information can be helpful to doctor, and they can do that very effectively. And additionally, latest cameras and other techniques are available that help medical industry to act accordingly and improve their diagnostic. So typically there are like four types of medical imaging terms are evolved. Like all the research are rolling around these four methods. Like one is like computed tomography, like known as a CT. Then another one is the MRI, like magnetic resonance imaging, MRI. And then X-ray fluoroscopy, and then ultrasound. So we can go what exactly this modality, like the modality of CT, like computed tomography, your body is going to be laid down. So there is like magnetic field is going to be crossing to your body, and we will get different kind of sections of the your body images basically. So we can capture the images, and then that image give you what part you are looking out, like abdomen section, or you are looking for your brain section, or depend on what kind of modality you are looking out. Based on the CT images are requested, and then that machine has a different kind of resolution, quality, other factors. So first one is like CT. Second one is like magnetic resonance imaging, which is like mostly suitable for the brain. Like if somebody has a brain tumor or some other details, that can be effectively captured by MRI. So basically that help you. But yeah, all the images are look again in the very dark. So how we can design our algorithm around that we have to follow up. Another one is like the X-ray, like the fractures, like hand fractures, rib fracture, or the leg fractures, like different kind of X-ray systems are available. So based on the X-ray, the different kind of characteristics are involved. Sorry. So different kind of X-ray resolution, the quality, how much dosage you have to apply, so that we can get better quality of X-ray image. So that technician will know, but typically sometimes we can get all the fracture related, other related information by looking at the X-ray. And then another one is like ultrasound. So ultrasound is nothing but like the monitoring your fetal, like fetal basically which the mothers are carrying baby. So with this, basically we identify what are the growth happening inside your fetal, and then that fetus basically give you all the birth child development, like how old he is, like how this hand and other moments. So that helps little bit about more uh, avoiding like premature or some other death related issues. So that's why ultrasonic is another challenging factor. So that is more important in our domain. So what is the image denoise? So like I want to give you like whatever the four modality we seen, all that having some kind of noise is automatically introduced. So it may be short noise, or it may be the saltpeter noise, it is a motion noise, or the patient which we are capturing his images, he is not in proper position. So we need to parameterize like how we can do different kind of approach so that we can get clear vision image. So that way we can understand. Like in this, I am showing one image. Like this is the original image which has short noise is introduced, and after filtering, basically after denoising, we able to see all the blood information, like the cell information properly. So for that, basically there are like different kind of image denoising algorithms are available. So you can use either a normal filtering, bilateral filtering, but here different algorithm has like different drawbacks. So like if you want to lose some of the information in denoising, it is not tolerated. So only the noise part is removed. That is always good. But if you hamper some part of tissue or some kind of culture which we are important, like looking for the diagnostic information, if it is corrupted by your algorithm, that is not accepted. So we are going to discuss one algorithm. That algorithm name is a patch based algorithm. So this algorithm is like most compute intensive algorithm. So basically what we are doing little bit of neighborhood calculation. So we are going more detail about this algorithm, but whoever interested, there is a paper available like this algorithm, like patch based non-focus. The paper is available. You can refer the more detail. But this algorithm is more suitable for most of the biomedical image denoising. So that, and it's like compute intensive wise. So that's why we selected this one to discuss today. So I can go a little bit of detail how this algorithm work. So basically, when we take a image, it is like in a small pixel area. So what we are doing here, like we are taking, this is my pixel, and this small filament I want to verify, is it noisy or non-corrupted or what exactly happening. So if it is normal, then we don't have like, we can see the straight line of the filament. But if it is a noisy, some pixels are get shifted by neighborhood border pixel, basically like 3 by 3 or 5 by 5, some pixels are get disturbed by the noise or some kind of. So what we are going to do, like we have to find out the similar pixel, like whatever the similar pixel, where it is shifted into the neighborhood. So that way we can identify that similarity, and then we can replace the algorithm. So like this algorithm work like this. Okay, this is my, this pixel, the center pixel I want to denoise, which is a 3 by 3 mask, and I can design this neighborhood patch. So this is my 9 by 9 patch. So what I am going to do, like this patch is going to be compared with all the parameter. So where I can find similar patch present into that image. So once I found a similar patch, then that patch is going to be have some kind of similarity measure. So we calculate the similarity measure between noisy patch and the neighborhood patch. So it is like this, like this is my noisy patch and the neighborhood patch. I'm calculating the difference between them. If the smaller difference, then the patch is like similar patch. If the distance is like difference is more, the pixel like that, this patch is not having any relationship with that. So that way, this algorithm is like basically verify how the weights are going to be formed. Like if it is similar patch or dissimilar patch, we are going to have more detail on that. So like that, I need to compare this patch with all like starting from my top pixel, then left top, exactly top, right top, bottom, left, right, except the center pixel. We are comparing all this patch and calculate the weight of the difference, like where we getting the difference of all the patches. And this all the weights, basically W1 to W9, it required to compare 3 by 3 pixel with neighborhood of 3 by 3, which is like huge computation is involved in this. So what exactly, and then this iteration is going to be multiples of like three, like first iteration to only one pixel. Yeah. So first pixel is like a 1 pixel boundary. Second is basically 2 pixel boundary. And then this is another like 5 pixel boundary. So depending on how many iterations you want to do, all the algorithm is going to be more compute intensive. So we can come back how we implement it on the GPU and everything. We can discuss more. So now I'm going to the, like yesterday we saw the video about CPU and GPU. So the theoretically, like if you compare the block diagram, so like in the CPU central processing unit, we have like control unit, then arithmetic logic unit, and some cache memory, DRAM memory, some other parameters. So like this is like single task coming, single task going out kind of uh, application. And the GPU, we have like the green indicate that small stream processor. So this stream processor, and like similarly, we have the cache, individual cache, local memory, DRAM memory. So if you compare top level, like layman word, like CPU is used for like central processing unit, and then GPU is like graphics processing unit. But it term itself says that it will be like little bit more about gaming console and other application. But with the help of computer CUDA like related application, we able to translate some of the application to the high throughput and high latency oriented application. How they are, like what background they are. Yeah. So basically today I'm going to cover most. Somebody, can you mute, please? Yeah, thank you. Yeah. So like graphics, we already discussed yesterday. So we already saw some of the example, like how the graphics is, the graphics processing is very popular in the GPU domain. So we use like the rendering, the games. Like this is a very popular game as a Doom, which is very popular and running on the GPU. Then this is another Quake 3. Then another. So the first GPU card is look like this, for which we having a small dedicated accelerator, we known as accelerator. And then second, the latest one, which is a launch last like 2018, this Ulta based architecture, which is like GB100, which is known as a GB100 architecture code, which has many cores. So currently, this GPU has around 5,600 cores. Like this small green color indicate that these are like small stream multiprocessors. So like many cores, and each one has their lot of different interface available. So like in single chip, you get all this information hidden. So the peak wise, like if you compare latest GPU with respect to the Intel CPU wise, like where we are. So like the throughput wise, if you compare like only 128 throughput on the Intel side, and on GB we have the 15 teraflops. So like it's more than the power wise little bit higher, but it's coming but with different aspect. We can have, if you are doing in HPC area, like high performance computing area, the minimum space can be occupied by the GPU. So that way we can save your per power wattage power requirement. And throughput versus power, like GPU is definitely giving more power. And due to the Moore's law, so now that like Intel is not able to put lot of transistor into the chip, so they are like bound to be have the Moore's law. So if they put more transistor, the power and weightage is going to be give like fire kind of symptoms. So like they are stopping to adding multiple cores. But in the GPU area, we are having separate architecture like for the each stream processor. So that way we can expand particular cell into the multiple GPU or multiple streams. So GPU is basically like add-on card. It is not uh, supportive. So like how your system will be look like. Why I am showing this one, like medical industry want all their applications running locally. So that's why I want to show you how this system will be look like. System is like typically you have the CPU and the normal parameter like the memory, whatever 20 GB or whatever the RAM you are going to use, and then hard drive, and it's dedicated PCI bus. So on the PCI bus, we are going to be attached our GPU, and then another NVMe, another interface. So basically, This all architecture will be driven by PCIe interface. So you have the dedicated desktop, which has all your system and other parameters. And then I can just skip this one. So the GPU wise, we saw like how we can do the programming for the GPU. So we saw the architecture, but we have to do the programming for the GPU. So NVIDIA introduced the CUDA, which is like Compute Unified Device Architecture, which is a programming platform for all the users. So whoever want to develop some applications on the GPU, so that can be useful for this. So basically it do all your multi-threaded application. So what do you mean multi-threaded? Like if you want to do one single thread, single application is going to be run on that particular CPU. But with multi-threaded, all the tasks can be handled by different stream processor. So that's like, so here, like in the CPU, you see the only a single thread, but once it is go to GPU, GPU form the multiple threads, like 1024 threads can form parallelly. So that same task can be run effectively on different stream processor and come up in a shorter duration time on the CPU side. So like typically execution model wise, like CUDA support various block, grid, and kernel, and some kind of more parameter. I can show you one example how exactly look like. So this example is which I am showing here, which is like simple C code followed by C++ conversion, little bit of like how the GPU code will be look like. So here I am doing vector addition. Like I want to do vector addition, which is like 1024 samples I want to add with vector A will be get added with vector B, and then result will be stored in the vector C. So like that kind of addition is here in this example. If I write down on the GPU will be do only the single line. There is no for loop, nothing is there. Only adding one parameter, thread. So thread index indicate that how many data we want to run, like how many threads I want to form. So that same code can be running on the GPU for many times. And typically NVIDIA, like the GCC compiler is used for the C++. So similarly, we have the NVCC compiler from NVIDIA, which can use for compiling your code, this code, and make your executable, like the out file or the executable file available onto the GPU. So if you have the GPU available, that executable can be run. So typically one block number of threads, like how many threads I want to do, and then do all the operations. So with this operation, like multi-threaded, all this vector addition can be done like way more faster with the GPU. So I am showing here like the comparison matrix. Like this is like matrix multiplication example. So like here we are taking the matrix size 16 cross by 16 so if you multiply two matrix A and B, typically how much time will be required. So the maximum right now we are supporting like 60K by 16K. So which is like very higher number. And the blue line is basically the cuBLAS library, which is from the NVIDIA. So which give you like high throughput value and with a shorter duration of the time. So if we are running the same thing on the CPU, which is basically not able to achieve like 1 teraflops also. So this application, like the whatever the CNN deep learning is implemented, a backbone of all the algorithm is cuBLAS. So all the operations are going to be designed by the cuBLAS algorithm. So typically how the GPU will be lit like, so this is like full GPU, but if you take only one stream processor, single stream multiprocessor, it has what level of support, like it support integer transform, other parameter wise like floating point operations, and plus we have new tensor core also added into this GPU. So tensor core is used for all your TensorFlow related application. So whatever you guys are studying like TensorFlow or the PyTorch, where we have the fourth dimension like X, Y, W, and then N is like another dimension. So that 4-dimension data can effectively operate it into the chip. So that help you to use all these applications. So another one is like more detail, how much memory each stream multiprocessor has, additional parameter, and then RT core, like we introduced another RT core, which is called as a ray tracing core, which help you to play additional real-time gaming. So if you want to use same GPU for your gaming application or shadow effect, or if you are fan of like various gaming, So that core also help you to do gaming as well as computational intensive model effectively with these registers. So going back to our algorithm, like whatever the GPU we discuss right now. So I want to implement same image denoising algorithm on the GPU. So before that, like I need to understand the flow. So the image like little bit very, the flow chart is like a very small in feature. Like I don't think like you can see all the inner name, but I can have next slide where I'm doing what exactly operation we are doing into this algorithm I am putting there. So basically what we are doing like the forward GAT, then the neighborhood distance calculation like the patch which we discussed earlier. So this is my patch. I want to compare with my neighborhood, and then this iteration is going to be run many times. And then we are having the final linear filter and reverse transform to get your image back, which is your denoise image. So let me show you. If we write the code and we profile it, like what kind of data need to go from CPU to GPU. So like the flowchart say that we have to read the image first. So I get an image, copy that image from CPU to GPU. Then GPU will perform the forward GAT, all the pseudo residue, then another parameter like the neighborhood distance calculation, weight updates, linear filter, and inverse. And then once all the operation will be done on the GPU, we will copy the results of denoise to the CPU and then write the image. Or if you don't want to write the image, you can display the image on your console or wherever you want. So when we profile this code, like the CPU code, like C code normally, so maximum time is spent on the distance calculation. Like 3% is used in other part, here 2% used in reverse part, like forward GAT, reverse GAT only 2%. But remaining 85% is going to use like all the CPU. If you use normal standard Intel CPU, 85% is used only in the GPU, and the remaining is on the 85% use only in the distance calculation. So they're like huge computation. So that's why we added all the part on the GPU. This is my CPU timing, GPU timing on the microsecond level. The image which I use is basically 2K by 2K. And then the speed up which I achieved by running this single application. And typically we get like performance speed up here with different applications. So and then when we compare with the different old GPU, because medical industry don't want to upgrade very quickly because the cost associated with each GPU is very high. So what they do typically, and additionally, like once they propose any medical equipment or medical algorithm, they need to get FDA approval. Like it's a food or drug approval. Basically, that approval give you is this product is safe for the human kind of operations or other things. So that's why they don't upgrade their GPU very frequently. So once they submit their proposal with particular algorithm with same GPU, they maintain that GPU at least couple of years, and then once it is stable, then they can upgrade their algorithm. So that's the way. So here I'm using like 2 years old, like 3 years old GPU, which is like GPU GTX 1080. So, and comparing with Intel Xeon is basically a multi-core GPU, so which we have the four cores are there, and comparing like for one image denoising how much time, then speed up is considering 1x, and then comparing with the GPU. So same algorithm right now performing 227 times faster. And then frame wise, like we can visually verify real time how the image denoising is happening. So I can show you a little bit more detail how the denoising will be look like. So this is my original image. Image acquired is 100 millisecond acquisition time, and this is a line where it is showing how your line profile will be showing. Like this line will be show how it is noisy. Like if you compare here, all this noise is introduced in this line. And after denoising, same algorithm applying Sapphire, we denoise the image, and then all the noise will be removed and all my tissues are properly preserved so that I can use that algorithm for my diagnostic purpose. And parallelly, like we use 10,000 images. Like here, I am taking like 10,000 images into the stack and denoising continuously. So like with that, we can see this image is like properly highlighted and verified. So how we can integrate this application? Like basically all the medical industries using their own tool. So we want like some tool. So like this is an ImageJ tool where they want to integrate same algorithm and show the proof of concept, like how the denoising is effective on the parameters. So like here, what we are doing like with the micromanager ImageJ and real time capturing the image from the camera, like from normal static image, like this is standard image which medical industry use for making analysis, so that if you work more lines properly, denoise properly, then it will be treated as a good algorithm. So I can show you like after integration, this is small video. So real time capturing the image and then denoising is already integrated on the GPU. So now I am doing this one. So the camera is capturing, which is like 100 frames per second. And I am turning off my denoising now, GPU denoising. Then you can see the image. Image is looking more whiter. So all the short noise or other noise are removed, and the frames per second is like 50 frames per second typically be achieved, which is like real time, more than real time. Human vision system like television standard is 25 frames per second. But with this, like the medical industry, we are having like almost 12, like 50 frames per second. And similar approach, like we have the APJ implementation, also the same algorithm, which is achieve only 4 frames or 5 frames per second, which is not nowhere near to the real-time approach. So with the GPU, we're able to achieve real-time denoising, and that is another example. So with that, yeah, done. Yeah. So this is like one example. Now we are going to another algorithm, like the feature extraction. Over here, I am using the Laplacian of Gaussian algorithm, and this algorithm is like more suitable for identifying the circle. So microarray images, basically the blood cells analysis and other things known as the microarray images. So in that, we have to identify how the blood cells are recognized, like the circles or shape, arbitrary shape, if they are not properly filled. So that algorithm is going to be recognized by this algorithm. So we are selecting this mathematical background a little bit. I can skip. This is again mathematical. And then algorithm look like this: take a image, normalize the image, generate the LOG, like the filter coefficient for the Laplacian of Gaussian, then apply your image convolution logic, like how to filter out, and apply thresholding so that we can separate out some of the non-separate parameter. Those are not required for our algorithm, and then enhance the circles where exactly the circle will be look like. Same thing like with the GPU implementation, which part is going on GPU, which part are going on the CPU. So that layout here. So I can skip a little bit here. And when we compare with CPU, GPU, and MATLAB, so why the MATLAB? MATLAB is again like research oriented field. So we come up with this algorithm very quickly. Like within a MATLAB, within a 1 hour, we implement this algorithm because the pre-allocated functions, like the functional MATLAB has a whole tool set, like toolbox. So all the toolbox has all the image processing and related applications. So basically we use that and get results quickly for the unknown image data sample. And after that verification, we implemented in the C++ code, verify if the C++ is like good way to implement. And then after that, we implement it onto the GPU. So that way we can consistently prove that our results are working on the three platform, MATLAB, C, and the GPU, and then count that circles. And the speed up wise, like still the GPU is doing good because we are showing like 100 times faster the same algorithm on 512 by 512 or 1024 by 1024 image size to be able to detect. But this algorithm has some limitations. So we want to seek more detailed algorithm. So we turn this feature into the another algorithm known as a difference of Gaussian algorithm. So basically this algorithm also give you same results, and it has special property of Gaussian filter is known as a Gaussian separable filter. So what we can do, like Gaussian filter is separable filter, means instead of doing two-dimensional filtering, we can do one-dimensional filtering. That save lot of computational time. So, and looking at this LOG and DOG filter coefficient, they are exactly look similar, and ultimately we are doing thresholding at the end of the making the accuracy wise. So if you compare both the shape wise, they are like almost similar, and it save your computational time very effectively. So we are putting that, implement the same algorithm on the GPU wise, 1D, 1D with row wise, 1D column wise, get filtering, come out on the CPU, and write into the file how many circles are detected, what is the dimensions, what are the parameters. So, and then after comparing this one, we compare with a different GPU. So the Jetson TX1 and TX2, which yesterday I show, the Jetson Nano, which is like small, handy GPU computer. So basically, all the medical industry wants like small handheld device as well, so that they can run very effectively and quickly solution. So that's why we tested on the same algorithm, and we able to achieve like 30 frames per second, like it's a real time behavior from this algorithm. So we integrated the GUI with this algorithm, how the GUI will be look like. So I can run this one. It will be show you like this is microarray image, and all the camera properties we are going to be setting here. And this is like my algorithm property, like how many spot, like the circle I want to decide. Based on the radius, we can change the radius of this blood cell. Accordingly, algorithm design his own filters, like what size you are looking out, and we give the adaptive threshold so that user can modify his threshold and detect different kind of circles. So I can show you, like running the code now and owning the algorithm. So all the red circle indicate that they are properly detected, and all the information like which one the numbering is here, and this will be show that how much radius, diameter, and other information required for the technician to use. And then he can change the threshold low and high so that it can get smaller circle. Like these are all not microarray data required, but we can play with different thresholding algorithm real time, and we can calculate and then give the results to entire system. So this is another example. Okay, now we can go into another part like hand finger counting using CNN. So basically, what is the purpose of this project? So basically, the goal is basically how to there is a like robot, like firefighting robot, and the firefighting robot has a camera, and we want to give the camera will get a image, hand finger movements, and then make a decision how we want to go forward, backward, reverse, right. So like that, we are going to design this product. So basically, what happened if I'm showing the finger number one, the robot will be moving in forward direction. If the finger two, it will be right, then left, like finger three, finger four is reverse, and finger like all the five palms I'm showing, then it will be stop. So that way, probably we can make some kind of effective firefighting robot which help you in kind of emergency area where the human cannot reach. So with the help of at least the cameras are like coming out, and we can verify where exactly you want to go, and we can have the two-way interaction with the robot. So and then for this, basically what we do, like we use normal web camera right now so that we can show the proof of concept, how the algorithm, and we are capturing all the image, at least 2 meter, 3 meter, how the resolution, like how my hand movements, like hands are captured, like fingers are captured, and then we can verify how this algorithm is effective or not. So, so we use like a lot, like last week and a few days you guys are discussing about CNN. What exactly CNN is? Convolution neural network. Basically, it's derived from human neuron, and then similarly we can have more adaptive nature, selective nature, how the features are going to be evolved. And then basically we have like the two different approaches. Either you can use feed forward or the backpropagation algorithm, depending on how you want to extract the feature. So that way we can control your algorithm, and then for training purpose we can use. And then another parameters like how to validate your handwritten or the finger count, so that that way we can verify it. So typically how the classification is going to work. So like if you say like hand finger classification I want to do. So typical classification is like in old days, what we do, like we take a input images, we do pre-processing, and then we extract the features. And then that features are known as a feature vector, and then that feature vector used for the neural network or SVM or some other model so that we can do training and then classification, so that we can categorize the results like it's belonging to what class. So what change with CNN happening now? CNN is basically will do everything for you, like whatever the feature extraction we are dealing right now. Take just give the input image, and then CNN automatically understand what feature you are looking out, like feature extraction, shift and distortion invariance, and then calculation of like classification finally, and then we can get classified output. So basically, layman term, it's like more self-learning introduced by the network in a convolution layer. So that's the way we can have more parameters. But it how it will be look like typically topology wise, if you compare CNN, you have the input image, then there is like called a convolution layer, is known as a feature map layer. So you have to design how much convolution layer you want to use, and in that you have to design select the mask size like 3 by 3 or 5 by 5 or 7 by 7, what convolution layer size you are going to be used. Accordingly, all the maps are calculated, and then we have the shift and distortion variants, like there is a subsampling layer known as a subsampling layer, and then that will be translate your image into the smaller dimension. Earlier we have the bigger dimension, then translate that image into the smaller dimension, and then same process is repetitive, like convolution layer, sub layer, and then finally fully connected layer, depending on what model you are going to be used. So here is like small example how the feature extraction layer is going to work. So basically take an image like 16 by 16 here I am showing here, and which having like 16 cross 16. That's why like I am input layer is basically x to 256. Basically all my image pixel are going to be translated, and all the layers are going to be feature maps, and everything is calculated, get on the weights and the bias, and we can decide that which character like A to Z, which one is recognized by this. So in the feature map, typically we are going to get, this is like some example only, but we can get more features. So basically either I can get edges for the alphabet, I can get horizontal edges, or the only vertical edges in this, or the background is subtracted. So this kind of different features are extracted. So how will be look like typically how the convolution layer will be look like. This is my image, and the convol width, this is my mask, which is a 3 by 3, which is also known as a Sobel one. So, and then we apply threshold, we can get this edge. So how this operation is happening, I can just show you here. This is running like this. All the neighborhood pixels are get calculated and multiplied by each and get replaced by center pixel. So the center pixel, like the yellow one, is going to be the replaced by every time, and then get a convol width parameters. So that way we can extract like one lines. So now I can show you like how my database, like is a very important part of the CNN is like a lot of deep learning or the neural network is the image database. How you collect your image database and how you club into different folders or different aspects, so that it will be easy for users to train your model effectively. So like here we are using like image resolution is 8-bit, height and width is like 640 by 480 or 1024 by 1024. All our color images is like 1 finger, 2 finger, 3 finger, different kind of samples. And then here we are using image digit, like NVIDIA digit, for getting the database and make a model like that, classify into different folder, and I can classify that folder how many image I want to use for the training, how many I want to use for the verification, and then testing. So accordingly we can do. So that way I can show you here. So what I did, like one folder indicate only 1 finger, 2 folder indicate 2 fingers kind of, and categorize into the 5 folders. And then after image digit, we can show all the parameter, like what are the different images. So for each image, I am capturing around 1000 images. So all the 5 other parameter. And then now on NVIDIA digit, like if you have the NVIDIA digit, you can just select the database creation folder. So I'm creating my own folder and giving only this database folder, which I am using, like the 5 finger database is known as a finger counting database, which has a 1, 2, 3, 4, 5 folders, and then giving the name and then assigning like how much percentage I want to categorize, like divide this image folders, 70% for the training, 15% for the verification, 15% for the testing. So with that, this will be like creating the another subfolder, like sub extracting the image name and then extracting the which images are going to be used in different categories, so that it will be easy for you yourself to train this data effectively. So like our headache is going to be reduced by this digit model, so that we not to categorize what how much image randomly he can select any 1,000 images which are there in the folder, and then randomly he can select 70% use for the training, 15% use for the validation, 15% use for the testing. So, so tools and methods, like how I use this CNN, like the CNN one. So like NVIDIA Digit, as I mentioned, like database generation is very effective, and we can normalize, crop. If I don't want to use same size, I can crop the image on that side. GPU, because I want to train the effective model quickly. That's why I'm using GPU tools. And then Cafe is another, before TensorFlow or PyTorch. The Cafe tool is like freely available. It's a university research project. Basically, this basically implemented in C++. So that's why advantage is like we can go back to the how they implemented weights and bias calculation. If something is going wrong, we can go into their code and modify it. Like sometimes in TensorFlow or as well as PyTorch, it's like limitations. We don't know like how they internally passing all the layer to layer information. If the hyperparameters are not properly set, that is not in our control. We have to rely on Google as well as PyTorch developer to give you accurate results on each layer to layer information. So we use Cafe here. So for Cafe, basically, we have to use like input image, design your convolution layer, non-military layer, pooling, and then this is basically standard AlexNet, which is like 7-layer network used for like most of the digit recognition and other parameters. So I'm using same parameter and I design my model. So this is like a Cafe script known as a Google protobuf file. In that, we have to write down which input image, which layer I'm going to be used, what is happening in first convolution layer, second convolution layer, and subsampling layer, and what are the features are going to extracted. So this is like the script look like. And then here I'm going to start the training on the GPU. So how for that basically I need to have my protobuf file. So this is my proto text file, and then which GPU I want to use. Like GPU 0 is like the first GPU I will attach to the desktop, and then I can show you my video here. So this is my protobuf file, which is like 7-layer, similar to AlexNet. Here, like each file has internal details. So see, convolution layer 1, subsampling, convolution, subsampling, all this written, and then I can go to the digit and then start my training by selecting like classification aspect, select my database, which is database. I need to select my hyperparameter, like all the training, epochs, iterations, all the hyperparameter, and copy my protobuf file. I'm pasting here my protobuf file information, so that all that network is going to be populated into the digit. So whatever the network I want to configure, like how much hidden layer, other information I am going to be used for my AlexNet is going to be populated and displayed in this graph. And then I will start my training. So giving the name, what model file, like once the training done, what name of the model file I have to save, so that that can be used for my classification purpose. So the training is starting now, and then like this is a GPU 1080, we can see here, and it start training. So this will be required. The database is like more in under different quality factors. So and color images are there. That's why it required around 6 to 7 minutes to train all these images. And then here like training is started. I'm showing like how the epochs versus error rate and learning rate is going to achieve. And then after training, now the training is going on still. Yeah, can show that it's on the GPU. So GPU show the percentage of utilization fully is training for all data. and now the I think training is done. So whatever the error rate I have assumed, that is going to show in this video. Yeah. So my model is trained, and then I get all that, like whatever the error I assume, each model values, and then model file is saved into the respective directory. So this is like one aspect. And then next one, like how after training, how I can classify, like by looking at randomly, either I can select any image or I can use a variation data. So verify, otherwise I can show you only single digit, how it is classified. So you randomly, I am selecting one finger and classify the results. This will be classified and it will be show you which finger is count. Like it's one, so one is having 100% here and remaining has low. And each layer, like whatever the convolution layer I have done, all the feature maps are properly shown in a graphical form. So that way, like if something goes wrong in intermediate layer, we can go back into that layer and verify this feature is important to you or not. Accordingly, we can retrain the algorithm again. So this is a way it can classify, and because of the 7-layer network, we can retrain and modify the algorithm and classify if your accuracy is not good, we can go ahead and improve a little bit more. So I can show you the next one now. With this, like once we do like our validation data and testing data, this is like testing data's accuracy, which is like for finger 1, we get 99% accuracy. And then for finger 2, 3, 4, which is little bit less accuracy. And finger 5, like all the 5 fingers are on, the accuracy is higher, like it's 98% accuracy. So why the question is coming, like why the 2, 3, 4 has less accuracy? Basically, I need to get more database. So if I have more database, then because and then human habit, like we are doing two finger by different approach, like either those 2 finger, this 2 finger, or those 3 fingers. So I need to get different combination of finger, how the fingers are treated as a 2, and then that way accuracy is going to be improved. So either I need to collect more image, put into the respective folder and train it. So that way definitely improve the accuracy for 2, 3, 4 classes. So with that we can go with medical image classification. Before that, I can take some questions if anybody has any doubt till now, because we covered like a lot of different aspects today. So just a second. Okay, anybody has any question, they can ask me.
Sir, Mahesh sir.
Yeah.
Sir, is there any background matters while counting the fingers?
Background matters. That's why like we are doing background subtraction for the initial image. So whatever the background we are capturing, we remove the background from all the image. Like we can save as a reference background, and then that background we use for subtracting from all the image. So that is another way to improve your accuracy. But in this, like with the CNN, background doesn't matter because we are treating same background for all the images. So that's the way background is automatically eliminated by feature extraction map. But if you want to improve your accuracy, we can put another algorithm like the background as a subtraction algorithm, which improve accuracy higher. So, yeah. So anybody has any questions till now, like for image denoising plus feature extraction, whatever we discuss, and then this hand finger counting before we going into the medical image classification? Because so there is like one question, difference between feature selection and dimensionality reduction. So there are like the different aspect of this. Like feature selection is if you are not doing a CNN based training parameter, then human knows, like we know that our database, what are the different features are important in your algorithm. So you can select that particular features. So that way you can save your timing parameter, like selecting the entire model wise. And the second one is like the dimensionality reduction is basically you have to use for the image size. Like my first layer, I'm going to have 64 by 64. Second layer, like I'm going to have 32 by 32. So the dimensionality automatically reduce. So that way we can verify how that image is behaving over the period of various operations. So, so there is like a different aspect of the reduction algorithm, like dimensional reduction algorithm. People are talking about 2D to 3D or sometimes rotations. We are going to have more details into medical imaging. Like I have the assignment on that. Over there, we are doing data augmentation, which is a part of dimensionality reduction. So we can discuss more in that. But the feature selection is like if you are doing DNN, the feature selection is only restricted by mass size and the kernel size. But without CNN, if you want to train your model, so you have the freedom to select different features, whatever important to your algorithm. If you reduce the image dimension of the image, definitely you are losing some of the features. So basically, depend on the what kind of reduction algorithm you are going to use. Like in image resize, like if you are doing 1K by 1K image and you want to downsample that image to 500 to 512, how much pixel you are going to be skipping? That is very important. So like after converting that algorithm, there is like bicubic, linear interpolation, some different algorithm involved. So based on that, if you are downsizing the image, it has to be enhanced appropriately so that you not reduce some kind of quality into that image. So, so we can get less accurate result in my term, because over the period of time we saw that if you reduce the image in shorter, some small size, even though you can get good training time, but quality wise, accuracy is like hamper. So in medical term, it is not acceptable, but other application like vehicle or other CCTV related application, that is acceptable, because there is like we're assuming to be continuous monitoring is happening. But in medical term, it is not allowed to lose the precision. So that's why like I'm calling, like there is another metric which we are discussing, which is like a cross correlation, like we call as a confusion matrix. So the confusion matrix deals this kind of aspect. So we can discuss that one in a couple of minutes. Yeah. So anybody has any other question? Which is good model accuracy, feature selection, or okay? There are like different. Uh, these are like different ways to measure the accuracy. So the model accuracy is like in medical term we are counted with different. I can tell you that name is basically sensitivity versus specificity. So we can calculate with a true positive, true negative, false positive, false negative. Based on that four terms, basically all the accuracy is going to be involved. And then that accuracy is basically in terms of medical, we always say that whatever the true result and positiveness is going to be considered as a high accuracy. So that way, because whatever you see by the algorithm, we have to give accurate results. It's not allowed to, like we are false negative, these are not acceptable into the accuracy parameter. So depend on your parameter. And otherwise, if you want to do with feature as versus dimensionality, so there are like some trade-offs are there. So user has to select which one is good for your application and other parameter. So but there are like new algorithms are right now, people are working on it. So it save your feature selection, because those are like already available. Only the dimensionality reduction is important, because they are saying the training time is taking more, how to minimize the training time. But in my opinion, I don't know, like it is good way in medical term, but other fields people are trying different combination. Okay, the question is like which selections are good, feature selection is better for mammogram classification. Or mammogram is like again the different kind of images. So in mammogram, we are categorizing the cancerous cell, like how it is infected and other parameters. So there are like different algorithm involved before selection, and we have to understand the doctor concern. Like by looking at our images, some of the tissue cell or tissue culture captured by mammograms are considered as like maybe the clotting of the some blood or some other things are different. So we have to get some kind of, if you are having good database of the mammogram, which is categorizing cancerous cells and the tumor into the mammogram, then probably we can get different slices of how much spread is going to have. So depending on, there are like geometric features people are talking about, the mammogram geometric features, then mammogram, the LB feature is basically local binary pattern features. So depend on different selection, accuracies are derived in the mammogram. So another question is coming. Yeah. Okay. Yeah. So okay. So this way, like there are like different aspects are there, but we can have more on that. So we can talk on that. But okay. Yeah. Any other question anybody has? So these are like good questions, I think. Yeah. But this term, like the medical, is like still evolving, like because of coronavirus and then pandemic size. So medical terms are like more important nowadays because all the research and everything is derived by that. So right now we are like the lung images, like lung cancer. Basically, the COVID-19 is infected to your lungs and giving you all the blockages. So basically, there is like one research going on the how we are getting more lungs images, so and then identify how much disease is spread or some other parameter. But research is still going on. It's like we don't get more images infected by the coronavirus patients, so we're not able to clearly say this is like a symptoms or some other parameters. So it is like additional. Feature selection is always good because you know that what features are important to your algorithm. So that is always good part. Dimensionality reduction is basically not recommended if you know the features, but people like for the research point of view, people tried whatever the available feature dimensionality reduction. That way you can propose by human selection like known feature versus dimensionality reduction, how much accuracy or how much parameter we can have that one. So that way. Mm. Yeah. Okay. I think anybody has any question before I start our medical image classification? Okay, one, two, three. I think no. Thank you. So we can go ahead. Yeah. So okay, I can show you now. Just a minute. My slides. Okay. So again, the medical image classification in same parameter like whatever the CNN model we discussed earlier. Like the first part is basically database for the training, testing, and validation. Transform the data into the like partition the data into like three categories, then architecting the CNN model, like how many layers and other parameter I want to use, and then more train the data model and testing for the new images, same whatever we discussed for the hand recognition, but here we are using like little bit new technique, which is like PyTorch and real database, which we getting from some hospital tie up here. So I can show you that. So like the MedNest dataset, which is like captured by the Dr. Bradley Erickson like Mayo Clinic, which is we have 60K images, which has different 6 categories. So six categories indicate that chest images, hand images, breast MRI, then head CT, abdomen CT, and CXR. So like different categories of the images are available, and it has like 10,000, 10,000, 10,000 only. The fourth one only the breast MRI are the less, but remaining all almost 60K image. All the image dimensions are 64 by 64, and then images look like this. So I can show it in the code again, yeah, but only for the small presentation wise. So here we are using PyTorch framework. Why the PyTorch framework? It's like mostly research oriented framework, and all the library like scikit and NumPy and other related libraries can be import and then we can reuse, and it has a better interface. And additional advantage is like if your machine has a GPU attached, automatically the PyTorch framework detect if your machine has a GPU and run the algorithm on the GPU. Or if it is not there, automatically use conventional CPU like whatever the CPU you have and run it. But the training time is like affected a lot. If you use same algorithm on the CPU, it will be required maybe 1 hour, 2 hours, or sometimes one day kind of training time. But with the GPU, we can train it effectively. So we categorize this data, like whatever the training data, into the three sub bucket, like training image out of 60K, I'm using 47K for the training, validation 5K, testing 5K. It's roughly like it's randomly selected out of all database, but we can change if you want more accuracy. So typically deep learning training network, how it will look like, taking my image here, like hand 64 by 64. So total gray values is 0 to 4096, like my input layer is like 0 to 4096. And then the gray values from 0 to 255 as my input values is a black and white image. That's why 0 to 255. All the gray set level, input layer, then all my convolution layer, intermediate, and the weights are calculated intermediate. And then we have the fully connected layer at the end, and the six classes, 1, 2, 3, 4, 6. So we are having the six classes. We have to categorize and then verify if they are going to classify accurately or not. So this is my typically convolutional layer architect look like. And if you want to use only image prediction, like the prediction algorithm is using like forward propagation. And if you want to get more weight update, like error is not enhanced, then we can use a backward propagation algorithm. So retrain based on the accuracy, improve your accuracy internally, so that that algorithm is going to be have more improved and more accurate features. So we can go back to Jupyter notebook example. So NVIDIA has, just you guys can see my screen now, Jupyter notebook. Anybody? Yeah. Okay.
Yes, sir. It's visible, sir.
Yeah. So here, like we have the some example. This is my data samples are available. So this is my images, all the images, and then data samples are here. Just a second. I don't want to download. Yeah. This is my data size, resize, abdomen, all the folders, breast MRI, chest MRI, all the folders. Data set is already uploaded onto the Amazon instance. This course is available in NVIDIA Deep Learning Institute. Like if you want to enroll, like there is like GTC, like GPU Technology Conference. That time these courses are free for all the researchers. So there is like instructor lead courses are available, but I am showing this one of the demo, which is very popular. So I'm going to show the data, then data is there, all the codes, images, and then this is some sample example. So this is my first assignment, which we are going to run with the Deep Learning Institute. And this is like Jupyter Notebook. So we have play here, the code we can run from here, each cell, and we can see the results at that time. So I can go through it. How is it going to happen? So basically, first we have to get the training model. So I'm going through the code, like whatever the library we want to load. So first is like load the NumPy library, OS, time, matplot used for the plotting, the graphs and image, and Pill library for the image processing, so that we can load the image, display the image effectively, and the torch, like the PyTorch, and getting all the CNN related information. And then scikit-lab, some other confusion matrix, property matrix, so that we can measure how the confusion matrix is calculated for the different classes. And here, if the GPU is available, automatically the GPU is going to be used. If not, CPU is going to be used. So that way, so I can click here and run my code. So automatically Jupyter node will be run this code, and it will be running, and one is indicate that this task is completed. So we'll load all this library, all the details. Now getting the database, we are getting the database. Initially, whatever the resized samples are there, I am deleting and then creating the new samples. And then once it is done, we are creating the same data with the resizing, like whatever the names, and categorizing and creating the label for each one. So we created like all the 60K image, 6 distinct categories. Sorry, yeah, sorry. Yeah, 6 distinct categories like the CXR, chest, CT, hand, the breast MRI, medic, head, chest, and the abdomen categories, all these details. And here I am going to the display randomly some image from that, so that you can see these are the real images are there or not. So these are the real images available, like chest, abdomen, hand, abdomen, then chest, then hand, some other. Yeah. And now this is a part like where we are converting the tensor flow, like how you're getting your data and normalize that image so that it between the 0 to 1, like all the gray values are like 0 to 255. We have to normalize so that for the scale the image, so that way the normalization is happening. So I'm normalizing that image. Here I'm just converting data into the rescale, into the like the TensorFlow format, because images are 2-dimensional. I need to read that image and make it available in TensorFlow format. So image tensor and class tensor. So that is taking some time. It is running on the GPU. So I can show you at the end if we have the running everything here. So star indicate in Jupyter Notebook, star indicate they are processing this block. So we can categorize training set, validation set, and testing set, and the rescale the data. Now here we categorizing that training images 47, validation, and this one. Then we have randomly allocating all the data where we is available, IDs and everything for the training. Now here we are architecting like how the model, like how your CNN model will be look like. So here the model name is MedNet. We are creating the MedNet. Here I am putting my first convolution layer, which is a 5. Convolution size is 7. Convolution layer 2, 10, and convolution size is 7, and some other like sigmoid and other activation function. And this is my convolution algorithm and all the parameters like the linear prediction, other parameter. And I'm using forward and parameter. So this is like here I am invoking all the model parameters. So model is created, which the class name is like MedNet, and I am going to use this one for my training. So the model is created. I'm using this one with my image height and width and class, like whatever the image height width I have, I need to connect that. The model is creating, and then now training of the model is starting. So before that, I need to understand the hyperparameter, like whatever the hyperparameters are good for my training the model, like learning rate, maximum epochs, like how much epochs really we want to use, so that data is going to be effective. Then the other parameter like the batch size, group size, like how many images you want to pass effectively. And this will be run iteratively. So all algorithm, unless I am not going to get all my iterations, epochs, and the error which I have put. So now I am going to start my training. It will be take some time. So training is started, and I will be see the results like each epoch level, how much training loss and validation loss I am accruing. So if the training loss or the validation loss is too much, it will be prevent. So the model is going to be overfit. So that is not good sign for your model, because accuracy is not guaranteed. So you have to again retrain by changing your parameter. So here like various epochs, iterations for the training and others are going on. Yeah, so validation loss is high, but it's like almost reaching 14 epochs. Like we are setting 19 epochs. Yeah, 20 epochs. Yeah. So I'm putting 20 epochs, but 14 epochs are there. Okay, whatever the overfitting is achieved, let's see how much accuracy we can get for my testing model. Like whatever the train model we run here, I am going to use same model file and then use the testing data randomly. And then let's see how much accuracy is calculated for the 5,000 images. So like this, we are getting accuracy like this. So accuracy is almost 99.52%. It's like very high. And this is my confusion matrix. Confusion matrix tells about how accurately you are classifying, like predicted versus true, how good you are in your parameter. So this one is like most of the best MRI classified with the best MRI. Here is like another like hand with hand. But whatever the misleading is like the head CT will be classified as a best MRI in certain cases. Or same case happening here like the hand is classified into the abdomen CT. So like this number has to be minimum so that like the lower part and higher part and the diagonally we have to get higher value is known as a place your confusion matrix. So the confusion matrix tells you about how good your accuracy model will be hold. So with this, we can try some other parameter. Like I am just checking randomly how the accuracy for the particular model will be look like. So some images are like not classified accurately. Like this is abdomen, right? This is a hand. This is not a hand, but this is like a different image. This is head CT, but there's like some misclassifications are happening. So what we have to do now, we have to either go back to our training model here, retrain the model. I'm doing again so that let's see this time if the it achieved without overfitting or not. Or it halted quickly. It's like quickly. Maybe I need to reset and then start from the beginning because it is coming like already the model file is saved. So that's why same model file is used and the epoch is like now about to reach 3 only. Let me see. Anyway, we can improve it a little bit. We can try because the same model file, either I need to reset my code, like I need to start from the beginning. Let me try again beginning so that it will be clear out my model file. It's called as a restart. And then, yeah, now I am doing this one. First model complete, second model part. Yeah, database is created, plotting, then TensorFlow conversion, tensor data conversion, come on, it takes some time here. My machine also making some noise because it's processing very high here. So my local machine also making some noise on this data sample. This is like the Jupyter Notebook has the tendency to keep the variable at the back end. So that's why the accuracy, which we are training multiple times, epochs are like preserved. So now let's see how it is going. It's still going on the training. Let's see. And then whatever the results coming, then we can go back to another exercise. Now we are reaching 17. Okay. At least still we are getting a little bit overfit, but it is okay. At least we are reaching more accurate. Let's see how the accuracy. Accuracy wise, like we are good with like 0.99, like almost 100%. And then let's see the recognition. Yeah. Okay. Randomly hand. Okay. And okay. So this is the way one medical image classification is working. So now what additional we have to do to improve this accuracy? So let me see if anybody has any question, then we can switch into that. Anybody has any question till this point, like how the Jupyter notebook and medical imaging is working? Medical classification? No, I think. Okay, then I can go with my presenting something. Yeah. So, okay. So now the second part of the same algorithm is basically data dimensionality and data augmentation. So what exactly you have to do is like change the data, because we have the limited data right now, 60K, but I don't want to go to patient and ask him like, give me the more images, again, the more symptoms. So probably what we can do with the help of computer vision and data augmentation, we can translate the image into the different dimensions. So I can show you here what I am saying. So here is like same thing, same data. We are not deleting the data samples right now. We are just using same data sample, like the name, and we are increasing like the 60K image. Now we are going to be make same data sample, like whatever the 60K image I have is going to be almost double, or at least 1.5 times higher with the help of data augmentation. So in this, like we are doing different kind of data augmentation techniques, like maybe we can do, sorry, so max root, or converting the data into the gray color, or rotation, transform the data, like take one image and convert that image into different orientation, like taking same image, base image, and convert that into the 4 to 5 different orientation, like rotated by 45 degree, 1 degree, 10 degree, or anti-clockwise, clockwise, both the sides. So that way we are converting one image data into the subset of data augmented parameter. So with the help of this, what you are going to achieve is basically improving your parameter. Like suppose while recording, like while measuring this X-ray image and the patient is moved, so that kind of activity we are considering by doing this data augmentation. So that way we can get some kind of advanced features, and then we can do another transform, like randomly we can add some kind of translation, like scale up, scale down. So we can move that image, like base image is going to be down, up, or the left shift, right shift. So we can translate the image into different orientation, top, bottom. So that way we can generate additional parameters. Then adding the noise. So like we are not considered to add the noise. So we can add some sort of noise into your database. So because right now, assuming that these images are good, so we can add some kind of noise database, like added noise, this one, like various intensity. So based on that, we can use same database and then try to use, like after normalization, we can try to use that image database and classify the images, so whatever the images we have. So right now we are going to have like more images, adding like each set additional images known as the augmenting class, because we have to give the labeling name. Like after adding that images, you have to club into the same folder and give into the proper naming, so that we can use for the classification purpose. So we can augment all the image name and then apply our categories, like whatever the categories we have, just join together so that we cannot miss new images which we are added. So like all the images, earlier we have 10,000, now all are going to be almost 15,000, 15,000, 15,000 images for each category. And then we can randomly display any image. So this one is like translated, and some other things are there. Like this is a translated again, these are translated. So randomly pick and then converting again our TensorFlow domain, and categorizing the data as a tensor. And then training, like similarly, whatever training we did earlier. So this is like next block is come on, it takes more time because image size are like now more. So it's almost 15K into 6. So that many images we have. So that's why the algorithm taking more time. So you can play around this code with various aspects, but as rescale value is done, categorizing into 4 set, 3 set training is 70K, validation 10K, testing 10K, same network. We can change around this convolution layer, other parameter. If the accuracy is not improved, you can add another play with this size, dimension relative size. So basically it's again the model level information. You can try it out. Then yeah, once model is done, model augmented model. I am saving the model file as augmented. Same parameters like whatever we use for the training. I'm training again. So training is started. Yeah, training is started. Epochs are coming. So with this, the accuracy is going to be reduced because we are changing all your algorithm approaches in next level. So, but we simultaneously need to change the hyperparameter. I am not changing any hyperparameter right now. Only database is added and the different types of images. So that's it. And let's see the how the accuracy will be coming. Like accuracy is good, bad, or what? Let's see. So training is good. Epochs are doing good. Yeah, I think yeah. Now it's going to stop with overfitting. Yeah, because the losses are yeah. Okay, and then let's see how the accuracy for this particular block. Yeah, so augmentation accuracy is 98%. So I already mentioned like 99 we are getting earlier, but 98%. But the classes are like very more. So like earlier we are having only 1,000, like now 1,500. We are getting almost 1,500. Each one is classified. So you guys can play around, understand the hyperparameter and other things in details. So with that, so I can take more questions if anybody has. So okay, yeah. With that, I'm stopping my yeah this one. So someone asking about sharing the code. If I share this code, even though you're not able to have the database. So right now the database is stored into the Amazon, like NVIDIA cloud. So that's why the database is available on the cloud. So I'm also running from the cloud. So either you have to copy that database, then this code is okay to use. Otherwise, code is no use. Or otherwise, if you have your own database, you have to modify some part of the code. So that will be useful for you. So, but the code is available on the net as well as if you enroll for the deep learning institute from NVIDIA, so that help you to gather more detailed knowledge. So that way I can show you what I am saying. So like yeah, so like the GTC, the GPU Technology Conference, like Deep Learning Institute is another NVIDIA's extension which we have. Like we train all the instructor base, like similar to my grade level or some other instructors are there. They teach you how the algorithm is working and they walk you through and they train about hyperparameter, other details. Only the basic knowledge is required like Python programming or C++ programming. So that way you can understand particular parameters. So with that, and there are like every year like a GPU technology conference held, and it has like different kind of deep learning and other various research related papers are published. So they are free for all academia. You can feel to join and attend the particular sessions as you wish. So with that, yeah, anybody has any questions, I can happy to answer that. Okay. Thank you very much with this. Yeah. Anybody has any question last time or otherwise? Yeah. Chaya madam.
Very nice session. Participants, any questions?
I think we have one question from Rajneet Singh, Ranjit Singh.
Okay. This thing. Okay. So like this is like proprietary database which I am showing here. Like the Mayo Clinic has tied with NVIDIA, so they share the database. But the medical imaging database is available on MIT BIH website. Like you can use the database. Like depend on your research. Like each has another one is a NIH repository where you can get health related other database. So it's depend on what kind of medical image database you are looking out. So only chest related are different, mammogram related different. So different categories are there. So you can just search it out which domain you are looking out. So some databases available, but again you have to sign up with their university. Like whatever the portal is available, you have to show them like you are doing this database only for research. Then they give you access, and then you can download freely because it's like human body related, another uh, safety concern from human specific. So you require to prove that you are doing some research on that, and then they release the database to you. Otherwise, like some like MATLAB or some other, everybody has some standard images you can use for your initial research. But if you want to show some good research related database, then you have to contact that portal, basically NIH, MIT, BIH, or some like it's a hospital oriented database, but they give you for the research.
Okay, actually, sir, some of the participants are asking for a share. Is it possible? Sorry, the code. Is it possible to share your code? That whatever code you are shown.
I can share the code, but it is no meaningful to them because the code is tied up with the database. So if the database is there, then only the code is okay to work. Otherwise, you have to do a lot of modification in your code. Like the Python notebook Jupyter library need to be tuned more so that you can get more parameters. So it's like up to you. So I can share the code, but it is no use. I don't think so. You can able to run it because the database is located into the server. So the size of the database is like around 10 gigs because the medical images are there. So 10 gig file size is there. So it's very difficult to download that data and then share it on some portal. That's why like we are putting on the cloud. So anybody is using cloud base, so we can access that data sample there.
Okay, okay.
Yeah.
As L Kanyakumari, this is what if you want this all these details. So we have the recording of this session. So very soon we are going to upload it on the YouTube, so you can get it from there for the future reference. And we will send the same link on WhatsApp group of the YouTube channel that we are going to upload all these videos. Okay. So as the sir said, so it will be of no use that code because it has some database connected to it. So for reference, if you need, so we are going to upload the video, so you can get it from there.
Even though like you can just search it on the NVIDIA's website portal, you can get the code also. Like some of the codes are like shareable, but the database is not shareable. So that's again, yeah.
Okay.
Okay, I think yeah, I'm taking more time. I didn't realize that timing. Sorry. Yeah.
Participant, if you have any question, please go ahead with the question.
I think no question. Everybody's happy with today's session because lot of interaction session.
Yes, yes,
So
yes.
I put like lot of details today, but I don't know like if they are useful up to you or your research. But it will be like lot of research is there, so you guys need to be do all attentions on different areas. Like not only so like image denoising is also one of the big aspect, and then feature extraction is also one of the good aspect. So I covered all parameters. So it's up to you select a particular domain and do that way.
Okay, I have one question, sir, but it is out of the scope of this session. So can I ask you a question?
Yeah.
Actually, in engineering, I was a very big fan of the NVIDIA, cricket game of NVIDIA. So,
Okay.
in that video, in that computer game, all the like Sachin Tendulkar, all the players were they used to mimic the original player. Like there were some actions of the original player. So, how it was possible for the NVIDIA to capture the actions of all the players and the mimic it? Was they using any particular algorithm or what?
It's basically it's like auto rendering we called. So we get particular features for the each player. So the we get that feature player, and then we call the rendering application. So it's known as a RT, like ray tracing rendering application, where we are extracting human feature like how he's acting, how he's doing the some mimicking, like his actions. So we mimic that and then put it into that character, like when we design particular game or anything. Nowadays, like if you see like Disney movies, so they are like creating more kind of scenic as well as creating action oriented.
Yes.
So earlier, like due to 3D, like we are like with ray tracing, the shadow effect and other effects are well enhanced. Earlier, it is not possible to get shadow effect, but with RT tracing, so the we remodel and render the particular points, like how many points are required for particular action to be manipulated and put it to particular character. So that way we can manipulate all the actions required from that gaming as well as real-time animation games or many aspects. Yeah.
Okay. Thank you.
Yeah.
I think we have one question from the L Kanyakumari.
Yeah. Meta heuristic for a feature selection. You can use the meta heuristic approach. Basically, it's like depend on meta heuristic has a little bit of more detailed oriented information. So user can have what time the image is captured or the what area orientation. It's like similar to for medical imaging we call as a DICOM format image, and then DICOM has more related information like age group, what kind of symptoms is recorded. So we can add additional features as a parameter so that we can club into the subcategories of human age group, human like what disease or what age, what type of symptoms is recorded or when we capture the image. So we can consider as additional feature, and then that way we can get more accuracy. So but it's like again, it's depend on your model, like how much model and how big model you want to design. So it depend on the your model parameter. I think that is the answer. But if you want more detail, I can definitely answer. But mostly which we are doing right now, meta wise, meta heuristic wise, we are getting more DICOM information available to user, so that that can be feasible to interpret and then use it for the research. Yeah. Yeah. Anybody has any question? Yeah. Thank you.
If any question, participant? Okay. Yes. I think this is, sir, one of the best interactive session what
Thank you.
that we have seen so far in the 10 day of FDP. One of the very best interactive session.
Thank you.
Yeah. Sir, can you share your mail ID? If
Yeah.
someone has question, can directly
I think
mail.
that yesterday I shared it again. I am sharing slide.
Yesterday you shared. Actually, some
Yeah.
participants are new today.
Oh, okay.
Yeah.
So this is like my email ID, personal email ID, official email ID. You can send it to me. Plus, additionally, my on NVIDIA, I am writing some of the blogs, so you can visit my blogs. So like it's like related to more NPP and NVJPEG related blogs. So those are also available. if anybody interested into the imaging and other domain, so that is also available. Yeah.
Okay. Think participant have no question. Actually, we are done with the question. Okay. So it was very nice session. Let me propose a vote of thanks. It's my privilege to propose a vote of thanks. Thank you very much for this informative session. I hope all participants learned and enjoyed a lot. Uh, it was really very interactive session that we have seen so far uh, in the so by FDP. So the whatever points you have covered, like the image denoising for the microscope images, like the CPU, GPU CUDA overview, then computer vision feature extraction of micro array images, then again hand finger counting using the deep convolutional neural network, like medical classification using CNN. So it was very deep, and it was having the very practical approach. So we could connect to it. So thank you very much for this session, sir. So over to Chairman.
Thank you, Mahesh sir. It was a very informative and interactive session. As our journey started from 23rd November.
Yeah.
So on Saturday, we are ending the first series of this FTP. But as Prabodh said, this is the one of the best and interactive session. So just by seeing the feedback, everyone is happy what the content you have delivered, theory as well as the practical knowledge. Thank you, sir, and hoping such type of cooperation from your side to the DY Patil Institute, sir.
Definitely. Definitely. Thank you. Thank you. It's
Thank
my
you, sir.
pleasure to
And I
give
think
this session.
sir, you want to say something to the participants?
It's my pleasure to talking to all the research oriented guys, and then I always interact with researchers, so that helped me to get engaged with what is happening in academia and what is happening in industry. So I love to help anybody is having any question, they can reach out to me. Thank you.
Thank you, sir.
Yeah, thank you.
Okay, so I think there is a night 11:30 timing there.
Yeah, it's 11 o'clock.
Okay, sir.
Okay.
Okay, sir.
Thank you.
Okay.
Thanks. Bye.
Thank you, sir.